Section 4-6 is on differentiability and continuity. And let me remind you of the objective of this section. It's to show that a function is continuous by showing that the function is differentiable. And you've worked on some problems now that you've been able to use that property, or it's contrapositive, and either given a graphical representation of a function, determine whether it's continuous or differentiable or both, or sketching a graph that has some particular features on it, whether it might be continuous or differentiable, or not continuous or not differentiable at different points. And now for the second half of this section, we're going to look at some problems here, an example in particular that looks familiar to us. Looks similar to a problem that you saw back in chapter 2, actually. And it says use one-sided limits, and that's a big hint as to how we're going to do this one. But it says use one-sided limits to find the values of the constants a and b that make the piecewise function f differentiable at x equals 2. And then check your answer by graphing. So back in chapter 2, when we learned the definition of continuity, we saw problems that were very similar to this, where they gave you some piecewise function, and that piecewise function had some unknown in there. I think they usually use k in their example. This one uses a and b. But the key there, or the question was, to find that value of k that makes this function continuous at this point where it changes from one to the other in our domain. And it's very similar to what we're trying to do here, except it doesn't say to make it continuous. It instead says to make it differentiable at x equals 2. So differentiable, remember, means that the derivative exists. So somehow I'm going to take the derivative of this thing and make sure that the derivative exists right there at 2. That's the changeover point, the transition point from one piece of this function to the other piece. But not only that, if you go back to the property you learned in the last, or the first part of this section, was that differentiability implies continuity. So if I'm going to make this thing differentiable, obviously I got to make sure the derivative exists, but also I'm forced to make sure that it's continuous as well. If I'm not continuous, then I'm not going to have differentiability. Differentiability implies continuity. In fact, if I'm not continuous, I know that implies that I'm not differentiable. That's the contrapositive. So there's actually two parts that we've got to work on this thing. I got to look at the continuity part of it, and I also got to look at the derivative part of it. And then once I get both of those two pieces taken care of, I'll make this thing differentiable at x equals 2. So that's just a little background of how you've approached these problems in the past and how it's similar to those types of problems, but there's a little bit more to it. So let's write down this function. It's ax cubed, and that's if x is less than or equal to 2. And it's b times x minus 3 squared plus 10, and that's if x is greater than 2. So there's our function. Now it doesn't matter which one of these two we tackle first. Again, I've got to deal with both the derivative as well as continuity. I'm going to deal with the continuity part of this first. But it really doesn't matter which one of the two you tackle first. And sometimes actually you might find the derivative is nice to deal with first, because sometimes taking the derivative might eliminate one of these unknowns. If you're just simply adding a on or adding b on to the end, if it's just by itself, when you take the derivative of a constant like that, of course we get 0. So sometimes as far as trying to find differentiability is concerned, sometimes the derivative actually might be a better way to start. But for this one, it's not going to matter, so I'm going to start with the continuity part of it. And again, if you go back to how we did these problems back in chapter 2, the function is going to exist at x equals 2. When I plug in 2, it says plug in 2 into the ax cubed part. I don't know what a is, but when I multiply a times 2 cubed, I'm going to get some number. So the function is going to exist. It's the second part of the definition of continuity that we had to worry about. And the second part of the definition of continuity said that the limit as x goes to 2 here, it has to exist. And so the only way that limit exists is if the limit from the left side of x equals 2 is equal to the limit as x goes to 2 from the right side. And that's what the hint they gave you there. It says use one-sided limit. So that's exactly what we're going to do here. It's the limit as x goes to 2 from the left side, which from the left side, that would be values of x that are less than 2. So that's the ax cubed function. we have to force that to be equal to the limit as x goes to 2 from the right side. And the limit as x goes to 2 from the right side, that's the values of x greater than 2, so that's b times x minus 3 squared plus 10. Okay, notice it's got a limit in here. Don't get lazy and not write down your limit notation. You need the limit notation in there to indicate what you're doing. So now let x go to 2 on the left side here. I'll have a times 2 cubed. I'll go ahead and write it that way. A times 2 cubed. We're just substituting in that value of 2. And we'll do the same thing on the right side. It's going to be b times 2 minus 3 squared plus 10. So we've substituted in our 2 there. And now let's just simplify this a little bit. So I'll have 2 cubed is 8a on the left side. And on the right side, you've got 2 minus 3, which is a negative 1. When you square that, you get a positive 1. So you get b plus 10 is all you end up with on the right-hand side. And so you can see that we've got 2 unknowns in here. So I don't really know exactly what a and b have to be, but I do know the relationship between them here. In order to make this thing continuous, as long as I pick values of a and b that satisfy this equation, I've got a continuous function. Let's go ahead and solve this, I guess, for one of these variables. I'll go ahead and solve it for b, since that looks like the easiest one to solve it for. I would have 8a minus 10 is equal to b. And we'll probably use substitution here. We'll get another equation with 2 unknowns. I'll have a system of equations to solve, in essence, and we can use lots of methods to solve that system. But as long as, in this case here, as long as I pick a and b so that it satisfies this equation, I've got a continuous function. But of course, that doesn't mean that the slopes are the same or the derivatives are the same as I come into this point. All right? It just means that I've got this thing continuous. So in other words, a lot of these values of a and b that I could use here would actually give me a cusp, which will not give me differentiability. So I've now got to look at the other half of this, which is I've got to make sure that the derivatives are the same from both the left and right hand side, or you can call it the slopes, I guess, whichever way you want to write this, but I'm going to write derivatives is what I want to look at, or I guess I can put slash slope on here just so you realize what we're actually considering here. So I've got to find, first of all, what f prime of x is equal to. Now when you're dealing with a piecewise function, the way you find the derivative of a piecewise function is by taking the derivative in pieces. Take the derivative of the first piece and then the derivative of the second piece and so forth for as many pieces as you have. So again, f of x was this function up here, ax cubed, and b times x minus 3 squared plus 10. So I've got to find the derivative of each of those pieces. So let's start with the first piece, ax cubed. Again, treat a as a constant, so the constant stays out front times the derivative of x cubed, that's 3x squared. I'm going to write that as 3ax squared. Usually put the number out front there like that. Now, the domain for the first piece was for x less than or equal to 2. But remember what we said, when we take a derivative, we lose the endpoint. So this is just going to be x less than 2. Now, our whole goal for this problem is to get that endpoint back. So I'm eventually going to find out the right value of a and b so that I actually am defined there as far as the derivative is concerned at x equals 2. But technically at this point we lose our derivative, or excuse me, we lose our endpoint when we take the derivative. All right, let's take the derivative of the other half of this, which the b stays out front, it's just a constant. And then the derivative of x minus 3 squared plus 10 there then is going to be 2 times x minus 3 to the first. This is a composite function, so we're following chain rule. And then multiplied by the derivative of the inside of which, of course, is 1. And add on the derivative of 10, which, of course, is 0. You can write those things down if you want to, but it's not really necessary. And this is on the other half of the domain if x is greater than 2. All right. Now, we have to do the same thing that we did up above for continuity, but we have to do this now on the derivative. So in other words, I've got to take the limit as x goes to 2 from the left side, which is going to be the 3ax squared, and I've got to force it to be equal to the limit as x goes to 2 from the right side of, I'm going to write it as 2b times x minus 3. I could write it as b2, I guess, if I wanted to, as I have up above, but usually we put that constant out front. Again, the key here is I've got to force the slope from the left side to be the same as the slope on the right side of 2, or that is the derivative on the left side to be the same as the derivative on the right side. So that's what we're doing with these limits. So go ahead and plug in 2. So we have 3 times a times 2 squared is equal to 2b times 2 minus 3. And so squaring 2 over here on the left side, that's 4 times 3 is 12a. And that would be equal to 2 minus 3 is a negative 1, so this is going to be a negative 2b over on the right side. And again, you can see how you have a system of equations. Again, if I just scroll up here, you can see our first equation was that we came up with was 8a is equal to b plus 10, which we solved for b. And I'm going to do the same thing down here, divide through by the negative 2, so I'll get a negative 6a is equal to b. And so now I have 2 equations and 2 unknowns. I have b is equal to negative 6a, and I have that b is also equal to 8a minus 10. So I'm just going to use substitution to solve this thing. So I'm just going to substitute in for b. Negative 6a is equal to b, which b up above we said is also equal to 8a minus 10. That's our substitution. You can also use elimination. Technically, you can also use matrices on these to solve. It's up to you on what method you want to use. But let's solve this thing for a. I'm going to subtract the 8a to get a negative 14a is equal to a negative 10. And solving for a, and when I divide by a negative 14, of course the negatives will cancel out. So you'll have 10 over 14, or that simplifies down to 5 over 7. So a turns out to be 5/7. And once I have a, I can go back to either one of those 2 equations to solve for b. I can either plug a in here, the 8a minus 10, and find b, or I can plug it into this one here, the negative 6a is equal to b. It doesn't matter which one, but I'm going to pick the easier one to do, which is the second one, I guess. So it's a negative 6a, which means that b is equal to a negative 6 times a we found out was 5/7. And so b turns out to be equal to a negative 30 over 7th, I guess is how I'll write that. And so there's our solution there. We have a is equal to 5/7, and we have that b is equal to a negative 30 over 7. And so let's see what happens. They said to graph our solution and see what happens here. So let's see if that in fact does give us the correct graph that's both differentiable and continuous. Oops, I didn't need to minimize that. And so let's go into our y1, and remember the way that you sketch a differential or a piecewise function like this is that you take the equation and you divide it by its domain. So I'm going to take 5 over 7 times x cubed. Again, we found out that the value of a was 5/7, and we're going to divide that by the domain. That's x less than or equal to 2. Make sure you put that in parentheses. And then for the other half, we found out that the value of b was a negative 30 over 7. And that's times x minus 3 squared plus 10. And again, divide that by its domain here. And that was x is greater than 2. Okay, so there's our equation. And let's just set up a window here so we can kind of see what's happening. I guess in particular we're worried about what's happening right around 2. You could look at more of this graph, I guess, if you wanted to, but I'm going to just look at what's happening at 2. Let's go from negative 2 to 6. We'll just get x equals 4 there centered in our, or x equals 2 there is what I want to have centered in the middle of my screen. And I'll just leave the scale there at 1. I guess I don't really know what the best choice here for y is, so let's use our table to help us out. We'll start it out at negative 2. I'm going to put this back into ask mode, and we'll have it changed by 1. So it looks like we're at negative 5, negative 0.70. So we start a little bit negative, and then it increases up to almost 6. And on the y2, it starts at 10 and starts coming back down. to negative 28. Well, I'm not going to worry about going that far down there, but it looks like if we go from about negative 6, you can go further if you want to, and I think it's got to be a little bit above 10 there. That's the first number I saw, but I am not starting right at 2 there in what I saw, so I'm going to go from negative 6 to maybe 12. We'll see what happens with this graph. So there's the first half of this, and there's the second half. Now if you look closely there, you can see there's a little bit of a gap in my sketch. And certainly if your calculator has difficulty sketching it, as it's having right now, stop and think and make sure that you've actually solved this problem correctly. There are a couple things you can do to try to help this thing sketch correctly. One of those things is to change your window slightly, if that helps it. Another thing that you can do, if you go back to your y equals menu, this is not guaranteed that this will help, but sometimes actually forcing it to plot a point at 2, since I put that at the center of my screen, both equations might help us with that. So I'm going to change this to greater than or equal to. So it actually forces it to plot the point right at 2 for y2. And let's see if that helps it. And there we get actually a much better sketch of this thing. It doesn't have the hole in the graph. Okay. So just realize that as you sketch these things, realize your calculator might have a little difficulty trying to sketch them, and it can be based on what your window currently is set to. Depends on whether or not it will have that problem. But there we go. That's our example that we needed to cover.